Oh, thank you, Lisa. I think Lisa's knowledge of the start is so much more than ours from coming in later, so you get a true insight as opposed to an Oz Minerals biased insight into how the discovery happened in the tectone. So Oz bought the project in about 2009, and this presentation just covers a little bit of the development work, but also some of the exploration work, because that's the area that I know more about. Considering it's an election campaign, not everything I say might be the truth, keep that in mind. Lisa sort of have covered most of this, but we'll quickly skip through. Carrapateena sits down here in the Gawler Craton, Olympic Dams up here, and Prominent Hills up here. Rudy Gomez with the PACE funding drilled the hole. And at the time that Oz bought the project, this is a good representation of what existed. The discovery hole sits here with the little red collar, CAR2 and the intersection that Lisa mentioned, and Teck in their joint venture did a number of holes, predominantly, in fact exclusively vertical holes, and drilled 80,000 metres of drilling before the sale process, and Oz came in. At that time no resource had been calculated, but as part of, if anything, probably our sales pitch upon buying it, we calculated a resource of 203 million tonnes at 1.3% copper. Since that time, Oz has continued a fairly aggressive drill out to increase the resource confidence and to move towards a pre-feasibility stage. As a result, another nearly 50,000 metres have been drilled up until late 2012. And Oz chose to drill with angled holes. We were probably a bit luckier than Teck in that we'd had experience drilling in the Gawler through cover, and so we were more comfortable drilling angled holes, and naturally for a vertical pipe-like ore body, the angled holes provided a lot more information. The upshot of that is the resource currently exists as both about 50% indicated and inferred, and the global resource, depending on your cut-off, sits at a total resource of nearly 300 million tonnes, or even the engineering side of the business is saying that a cave to 0.5 and possibly even 0.3 cut-off is really feasible. So once those cut-offs start to be taken into account, it's starting to become a pretty significant deposit at over half a billion tonnes. So this is a slide that shows that change from when Oz inherited the project to how it exists now. The drilling, the vertical holes that Teck had drilled showed that suggested that there was two bornite zones surrounded by a large chalcopyrite zone, and there was a zone actually in this, we called it the exploration target at the time. This is where the discovery hole was. It took 36 holes, as Lisa alluded to go from drilling the discovery hole in this area here to hitting this sort of 200 by 200 metre zone of mineralisation that carries the bulk of the resource. When you read the OD case history, there was a large number of holes, at least 3 I can think of, that drilled the centre of the gravity anomaly before they hit into mineralisation. It seems to be a real challenge in ASEG systems to go from discovering the system to working out whether there's some payable grade within that system. The angle holes, as I said, made a really big impact on our ability to understand the system and to hang areas of grade together. And as a result, we now have a connected, really high-grade bornite zone with consistent intervals of 40 metres at 5% copper and 40 metres at 6% copper in a number of holes. A really nice high-grade core to the system. And that's surrounded by a chalcopyrite zone in hematite breccia, and the depth is only constrained by drilling. We're down about, I think you'll see on the screen there, we're down about 2 kilometres from the surface, 1,500 metres of mineralisation, and there's no sign that it stops. So, as Ken mentioned development, just a couple of things on development to explain where we're going. We were full steam ahead on an exploration decline. With the cycle changing, we've pulled back just a little bit to a pre-feasibility study. But the decline is planned to get down to the level of both. This is 480 metres below the surface, and an exploration decline means that we don't have to drill so many expensive holes to get the confidence that you need to design the cave that will be required to mine it. So the current focus is on doing a pre-feasibility study that includes a decline to get down to do infill drilling to set up your cave. And I show this, and particularly I show the machine that's planned to do it because it's of interest for some of the geophysics that's coming up later. This is a tunnel boring machine of the same design that is going to be used to do the decline at Carrapateena. The re-engineered one that we have bought is worth about $30 million, and it actually works by using these grippers to grab a sidewall and push against that and push itself forward. And the implication of that is if you have faults much wider than that, they can't grip, your machine gets bogged. And that's just of interest for some work that I'll talk about further on in the presentation. So onto the area that I know more about. This slide was actually sent in an email to stir up the geo at Carrapateena originally. But in giving this presentation, there's actually a pretty valuable lesson in this. The geologists provide far more than just a registered image. So it's a little bit unfair on the geology, but you are looking at random slices of outback South Australia over all of the ASEG deposits there. And if that's all you had to look for ASEG mineralisation, you're cooked. What we can provide as geophysicists is images of the subsurface, including the gravity on the right, and Carrapateena sits here and Carmsen sits up there. So while it's very tongue-in-cheek, it is pretty important to understand that without geophysics you couldn't explore for ASEGs economically in South Australia. So the work that we've done since we took over it initially involved reprocessing of all the data that we got from tech. We reprocessed all the MT data. Rob Angus is in the room who did that work for us. Dave McGuinness reprocessed all the IP data, and we did new 3D models. We did go and have a look at the radial IP data because I was particularly interested in that, particularly for the chargeability more than the resistivity. And you see some very, very strange polarity behaviour in that radial data. We spent a few hours looking at it and moved on. It just doesn't make sense. So one of the first things that came out of the data was the similarity in amplitude and size between the Carmsen anomaly and the Carrapateena anomaly. I don't quite know at the time why I mentioned 2 decimal places for the residual anomaly, but the point is they're near identical. And this slide and the 2 that follow it are lifted from the target, lifted from the presentation that proposes we drill Carmsen. So I haven't changed anything. I've just picked the 3 slides that show why we were so keen on Carmsen at the very start. So the similarity in density is pretty obvious. The inversion of that, and this is another lazy inversion, sorry Chris, but as you sort of alluded to before, my experience is you just really focus on the centre of these things and don't get too much worried about where your anomaly blows out until you've got enough drill holes to really question that. But one of the 2 tech holes on the side had drilled down here, and when we went out and looked at the core, there was barren hematite breccia. Not greatly developed, but there's about 50 metres of it, predominantly granite and granitic breccia in that interval. And so we were pretty excited about this. That meant, using Occam's razor, the most likely explanation of the rest of the density is hematite, and if it's hematite, well then there's a good chance that it's going to have economic sulphides with it. The depth of basement is about here, so these shells are just too low to really map it. There is an anomalous mass that goes into the cover that even today that we haven't explained. We haven't had a drill hole in the right spot to answer that question. So we compared that with the exact same inversion at Carrapateena, and once again the depth of basement kicks in about here. The green lines on this are the copper grades. The reds and pinks down the hole are just hematite breccia or hematite alteration. And we proposed at the time, well, what if the tech hole, and I should mention, sorry, that the reason the tech hole is not drilling the centre of the anomaly is there is some heritage issues in terms of getting clearances and the like, so you have to be a little bit careful. So no one has really had a straightforward run at just hitting the centre of this density anomaly. Maybe Lisa can comment later, but that's the reason, as I understand, why the two tech holes are off to the side of the anomaly and not in the centre of the anomaly. So we proposed that, what if the Carmsen 2 hole is an analogy for the Car 44 hole drill on the side, and we all know the answer to the story. It is, but this work sat there. We did this. We got really excited about it, and then we had to wait for 18 months. The focus was on drilling out the resource, and especially building up our heritage relationships and our farming relationships with the landowners. And so Carrapateena being bought to be our next development project, all the effort was focused on getting towards that development. So we were there sitting there pulling our hairs out as really excited explorationists, saying, well, look, we think we've got another one, and you sort of ramp up the conversation a bit more. This is good, but you don't want to be over-promising, but you want to get out there and drill it. So you sort of really set yourself up for a pretty big fall when the time comes. But we were more convinced than I've ever been that it was going to be explained by hematite. It was just then a question of whether there was economic mineralisation associated with it. So this is from one of the announcements on Carmsen, but the first hole we drilled from one of the old tech pads, which is why it's such a long hole, and it's a fairly shallowly angled hole. It's Carmsen 3, and Carmsen 3 hit ASEG alteration essentially from when it went into basement all the way down to the end of the hole. There were zones of slightly better grade that are mentioned there, and broad, pretty reasonable grade in the scheme of things, 0.43% copper over the length of it. And we knew straight away there we're on a system. We saw bornite mineralisation, chalcopyrite mineralisation, so some of our fears are raised about whether it was likely to be economic. And then after that, it just becomes a challenge of drilling these things out to define where the centre of the resource is, and if you've got 1 billion tonnes at 0.1 or 200 million tonnes at 1% or whatever else it might be. So some of the follow-up drilling after hole 4 had a few difficulties drilling. It ended up with a third wedge on it, and you can see a good interval there of about 0.4. So we were sort of groping around the system in the same way that Tech was when they first came to Carrapateena. And as I presented in my talk at the ASEG, the geophysics being dominated by the iron oxides, both the potential field properties and the electrical properties, in my personal experience, don't add a lot once you're inside the system. You're really forced to, I say forced, sounds like a bad thing. Your geology drives it once you're inside the system. And we're a bit lucky, having owned Prominent Hill and having spent a bit of time at Carrapateena, and instead of taking 36 holes, it's really only taken sort of 10 holes to get a much better handle on where to go with the mineralisation. And yeah, that's, I think, advantage that we had over Tech, is that we had experience in this deposit type in this part of the world. And the best hole to date is the recently released in our last quarter, 700 metres at 0.83% copper in the hole here that goes above hole 6. And there's plenty more drilling to do, but there's not too many holes into ASEG deposits in South Australia that have those kind of intervals at those kind of grades. The only other 3 I can think of are resources, and 2 of them are mines. So we're pretty bullish on this, and we're pretty happy. It's our eureka moment, if you take the theme of the conference. Sorry, one more slide I pulled out of the presentation just to give you a bit of an idea of the section. You can see the density anomaly, put another hell of a lot of cover on top of it. This one is constrained to the top of cover, but you get a sense of the grades associated with the density anomalism in this. As well as the ore body that sits down here on this density anomaly, there's drilling at the zone called the Saddle and at Fremantle Doctor here. Tech drilled a couple of holes which are in grey, and we've since drilled 3 holes, one of which hits a large low-grade intersection, as well as nearly 90 metres at 1.5%. So there's some pretty good mineralisation over narrow intervals, albeit deep. So the age-old chestnut comes up about, what if there's ore bodies in here that are hidden due to paleotopography? And I was really encouraged to hear John talk about quantifying the cover, because quantifying the cover is my pet topic in looking for these kind of systems. as part of the interpretation, it became really critical to use the downhole seismic information we collected, the VSPs and the sonic logs. We actually had to invert the polarity of the seismic data due to the really high velocity quartzite at the top. But you could see from the sonic logs, you could pick a number of really noticeable breaks, and you could correlate them to certain positive or negative reflections in the seismic data. And that took a lot of time and effort, particularly for Tom, who's not here, who had to do the work. And without that, we wouldn't have had a very effective mapping of the cover. But by doing that work, we actually got quite a successful result. Thank you to everyone at Oz Minerals, particularly the exploration team that I work with, and the likes of Rob and Dave McGuinness and Peter Fulliger and Glenn Pears, and there will be people I missed out, but thank you to everyone who's put work into contributing the exploration that we've done at Carrapateena.
That's great, Charles. Got time for a question or two? Steve.
I can probably just yell it out. I was just wondering about the geometry of those IP surveys that comes in, and were they 200 metre dipole? What was the geometry that you're using?
So it was the tech data, and it's 400 metres with a 200 metre receive, I think, isn't it, Lisa? I'm pretty sure it is. It's 400 metre transmit. Yeah, 200 metre receive, I'm pretty sure.
Hi, Charles. Love the work about the paleo surfaces, or modelling the overburden. But I wanted to ask about the Bouguer gravity correction, because we're sort of making an interpretation about what the density of the rock is between where our observation is and the RL line that we choose, normally 0. How does that affect your overall resultant picture? And do you do anything to overcome that issue of potentially getting the interpretation wrong in the Bouguer correction?
Yeah, so we've done a bit of work on that. We've played around both trying to create variable cover density maps and correct for that, and we've also just played around with letting a statistical representation of the cover define what it's going to be, and we found that it's 2.47 is the best correction for this data set. But the upside story is ASEGs are dense. I did a presentation on Prominent Hill internally a couple of years ago called How to Hide 200 million tonnes at 28% iron, and the answer is you can't. These things are dense, and it takes a lot more than that subtle change. You can play with your geometries, of course, and it gets there, but the way, having looked at the deposits that we have and the prospects that we've worked on, you can't hide a significant accumulation of iron. We don't have a set formula for doing it. I think we play. When we get a good fit to our data and we feel comfortable explaining it, we sort of don't think about it. And if someone drills a hole or we look at it and it just looks to correlate with the topography or something, we then go and investigate it. We don't have a rule of thumb, but we just play with the data until we think we have a reasonable geological representation.
I've read some really good articles recently which show seismic tomographic imaging of igneous intrusions. Now, I just wonder whether the velocity contrast of your mineralised zone would be appropriate to try seismic tomography.
We thought exactly the same thing, and we did some work on it. Admittedly, we don't have a large number of samples, but from the petrophysical work we did at Prominent Hill, not at Carrapateena, it showed that the contrast between the iron oxide with sulfides wasn't particularly anomalous or wasn't really anomalous at all from the iron oxide only rocks. And that it was a thesis that I proposed at the conference, that all the density, magnetics, electrical responses and acoustic responses, in my experience, are dominated by the iron oxides in at least the Gawler ASEG systems. And I haven't yet seen or come across an effective discriminatory tool once you're inside the alteration envelope.
I get the last question. Would you think this sort of system would be suitable for downhole gravity survey? Density being so important, get closer?
I'd absolutely love to do that. We looked into it a couple of months ago. The other way of effectively doing that, whilst there's not a system out here, is thinking of 3D seismic. The seismic response is essentially a function of density, and we might possibly have precise, with all the obvious issues that, well, not issues, the geometry effects of doing the array, but you've got a chance of distinguishing 3D density down to significant depths, and it's something that we dearly love to do at CUMS and is in discussion with different people.